Welcome, everybody, to a hopefully short and sweet explanation of how to deal with these normal approximations to the binomial. I know it can be tricky, especially when they have the ones that are asking you to deal with just percentages and not actual numbers. It just doesn't feel right. But once you remember how to calculate means and standard deviations of these binomial distributions, which are pretty simple formulas, you'll see that it's quite easy because you just have to keep remembering that we are creating a normal curve approximation to the binomial. So we need to take our binomial data and transform it into normal curve data, means and standard deviations in terms of a normal curve. So let's look at this example where they tell us 87% of people actually show up for their flight on time, and because of this, airlines tend to overbook flights because of that 13% that don't show up. A random sample of 221 booked passengers is taken, and whether or not they show up on time is recorded. So we can see this is a binomial distribution because we have a set number of trials, 221. We have a known set probability of a success, 87%, where a success, in quotes, is showing up on time. And then we have basically only two options. Either they did or they didn't show up on time. So those are the kind of the key characteristics that tell us that we're dealing with a binomial distribution. So if we want to list the given information, well, we can see that P is 87%. You'll know it's P, not P hat, because we're talking about the proportion of the population. In this case, the all 221, right? Or, of all flyers, not just the 221. And then our sample, lowercase n, is 221. That's how many passengers we've sampled from the entire population of all flyers. Okay, individual, variable, and all that kind of stuff. So the individual, right, is a randomly selected booked passenger, because an individual just means each individual object that is being measured. Right? And in this case, it's each individual passenger that we're seeing whether or not they showed up on time. And then the variable that's being collected, right, is basically showing up on time or not, right, whether or not they showed up on time. And then the wording in context for the random variable is as follows. And I know these can be confusing with the way they word these things, but the random variable x is... So when we're doing a binomial distribution, we always ask questions like, what's the probability that x is less than 12? So x is considered a random variable because it can take on different values. It can be 12. It can be 11. It can be 43. And if you're taking a sample of 221, it can be everything from 0 up to 221. So that's why it's a random variable, because it's random as to which one of those numbers it is, based on the random sample of people you take and then count up how many of them showed up on time. So x is going to represent the number of successes, right? X is always the number of successes, and in this case, a success is showing up on time. So that's why x is the number of the 221 randomly selected passengers that showed up on time for the flight. Okay, and then how would we describe the P hat? Well, it's the percentage of our sample now that show up on time, whereas up here, P without the hat, right, just regular P, which we often actually use the Greek letter rho, by the way, which looks like a P. This is the percentage of all passengers that show up on time. And then the P hat, remember, is going to be something that we're going to compute from just our sample, which might not be 87%. That is the percentage of the 221 randomly selected passengers that showed up on time. So it's our sample statistic that we're going to see if it matches the population parameter of 87%. Now, can we say it's approximately normal? Well, yes, we can, because we have to test all of these things, remember? So when we're testing for a binomial and seeing if we can approximate it with the normal, there's a few things we have to test. The first is that n times p has to be greater than or equal to 10. And in this case, we take n, our sample of 221. We multiply it by p. You'll notice it's p, not p hat. So we multiply it by the population percentage of 87%, we get a number that's much bigger than 10. And then you have to do the same thing with n times q. We normally call 1 minus pq. It's its complement, right? Because probabilities always add up to 1. So if p is 87%, q is the complement of that, which is 13%. And if you do 221 times 13, you see that it is still greater than or equal to 10. So it satisfies that. We have n is a really, really big number. And you're kind of like, where the heck did that come from? Well, you can see it comes from down here. So they're basically just saying if they don't tell you how large n is, and remember capital N is the size of the entire population that we're looking at, and we're looking at all airline passengers. And if you know anything about the airline industry, I mean, there's literally millions and millions of people fly every day. So even if this was, how many people show up on time in a given day, it's going to be millions. So you could use a number this big, which is 1 million. So our population size is 1 million. Unless the question told you what it was, then you would use that. And that is greater than or equal to 4,420. You might be going, well, where the heck did they get 4,420? Well, the last stipulation for us to be able to be allowed to use the normal approximation of the binomial is, in addition to the whole NP being greater than or equal to 10 and NQ being greater than or equal to 10, we also have to have the stipulation that the sample that we're taking has to be 5% or smaller than our population. We can't take more than 5% of the population as our sample, because then it skews the independent assumption of each trial, right? That it'll continue to be 87% for each new person that we're testing. Because if you take too big of a sample, it's going to skew that. It's kind of like taking too many cards out of a deck of cards. All of a sudden, the probability of the next card having a characteristic is far different than when you started, because you're starting to remove cards from the deck. Okay, so again, where did 4420 come from? Well, it's a simple calculation. We're basically solving backwards for how large would the population have to be such that 221 would be only 5% of it. So we are basically setting up a simple equation of 221 is 5% of what, right? And solving for what? So you could either multiply by 100 or just change this to a decimal. So we're basically saying 221 equals 0.05 x, because that's 5% of some unknown. If we divide by 0.05 to solve for x, that's how you get 4,420 equals x. Okay, so that's where that number comes from. So they're basically saying as long as the population is larger than 4,420, then we know that our sample of 221 is less than 5%. Because if it was 4,420, it would be exactly 5%. And then anything bigger means ours is a smaller percentage. Okay, so now that we have checked that we have satisfied all of the rules that allow us to use the normal curve to approximate the binomial, we can actually do that. We can actually do some approximation using the normal curve. So the first thing they ask us is, what's the probability that at least 90% of the randomly selected booked passengers showed up on time? Well, we need to be able to have a normal curve approximation. We have to have some sort of normal curve. And to have a normal curve, right, we know that the middle of it, oh, this is a terrible drawing, is the mean. And then we have to come up with whatever the standard deviation is. Well, that means we have to be able to calculate these things based on our binomial stuff. Well, the mean of a binomial is simply n times p. Your sample size times your probability of a success. and then your standard deviation is the square root of NP Q. And remember, Q is just 1 minus P, so sometimes you might see it listed in other sources, textbooks, or whatnot, as N times P times 1 minus P, square rooted. All right, so we need to calculate both of those. Well, remember that our N, the sample size of this particular example, is 221, and our P is 87%. So we know that this is going to be 221 times 0.87, and then our standard deviation is going to be the square root of 221 times 0.87 times 0.13, and then take the square root of all that, so grab your trusty calculators and calculate both of those, and you should get these two results. 192.27 and 4.995, blah, 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 almost 5. Now, you're going to see here in a second that we want to keep as many decimals as possible to keep our answer as close as possible. We don't want to round on top of rounding. So like you don't want to take your standard deviation and round it up to 5. You really don't even want to take it and round it to, let's say, 4.9951, right? Take this 9. You really want to keep all of those decimals if you're going to do it that way and type it back into a calculator or back into technology. But there are ways to actually put this whole formula into whatever technology you're using so that it will calculate it and it will keep as many decimals as it can, depending on how big its memory is. And its memory is probably pretty darn big. Even a basic calculator probably keeps something like 50 decimals in its memory. So you're going to get a much more accurate answer if you can do that. Okay, but in any case, we did the mean, we did the standard deviation, so now we have the shape of our normal curve approximation with those two things, right? We now know that the mean is 192.27, and I'm just going to write approximately 5. We're not going to use that, but I just don't want to have to write this big old number a million times. Okay, so now how do we calculate the probability that at least 90%, right, of the randomly selected passengers show up? Well, I always like to draw a picture, right? And 90%, we know the center line is where the mean is. That's always 50%. So we know 90% is going to be up here somewhere, and at least means greater than 90%. So this is what we're looking for. We're looking for that area under the curve, because area under the curve equals probability. Well, we need to know what that cutoff is as far as what is the x value, right? Because remember, we're always talking about x values, the random variable number that gives us 90%. Well, that means we got to take 90% of 221. So 221 times 90% is going to give us 221 times 0.9, 198.9. 198.9. Okay, so now we know that we're basically asking the question, what is the probability that x, our random variable, is greater than or equal to 198.9 on our normal curve, where we have an average of 192.27 and a standard deviation of 5. So if we were going to calculate our z-score, it would be our x value, right? 198.9 minus the 192.27, because that's our mean, and we would divide that by the standard deviation. Again, I'm just going to do 5 to make the math easier. And that gives us a z-score of 1.326, roughly, because obviously we've rounded our standard deviation by quite a bit. So that tells us that having at least 90% show up on time is 1.326 standard deviations above the mean. And just using the empirical rule, we can kind of think about how small that is. But then we could also go to a z-table, and we could figure out what that is, and so on and so forth. Or, better yet, we can just use technology to do all this, because that's really what we want to do, is let technology do the heavy lifting. So first we can look at how to do it with a TI calculator. Okay, so we're trying to find, remember, we're trying to find that area under the normal curve. So we're going to go to our distributions menu, which is second vars for variables. That brings up distributions. And we're on the normal curve, so we've got normal PDF or CDF. PDF is when we're trying to do the probability of it equaling. So x would equal, 198. We don't want that. We want greater than or equal to. So we need to choose 2. Now the nice thing about the TI calculator is it lets you find probabilities in either direction. A lot of other technology will always default to just giving you what's called a cumulative sum, where it always sums from the low end up to your number. So if you did, like for instance, we're going to do it in Excel. When we do it in Excel for 198.9, it gives us the probability of being less than or equal to 198.9. It always does everything to the left side. But here, with the fancier TI, it asks you for a lower bound and an upper bound, and it defaults to this -1e to the 99, which basically just means negative infinity. So we don't want that. We want our lower bound to be our x value of 198.9, right? And then our upper value is going to be, like positive infinity. So we're just put in a whole bunch of 9s, right? Just make it a big old lot of 9s. Because that'll be, as close to infinity as we need to really get. Okay, now the mean has to be the mean that we calculated, which is 192.27. And then the standard deviation, instead of putting in our approximation of 4.999, we can actually do the computation. We can put in square root of 221 times 0.87 times 0.13, close the parentheses, and then go down and paste it. And what it does, see, this is a fancier TI-84 Plus, then it pastes it inside it. Now, if you have the older version, which just gives you the, when you go and hit normal CDF, it just puts normal CDF and then a parenthesis on your screen, and you have to type the numbers in. Just know that what it wants, right? So you've got the normal CDF, right? And then it'll have this. The first number you give it is X, i.e. the 192. And then, if you look at the numbers here, right? Go to the left, you'll see. So the first number they ask for is the lower bound. I'm sorry, not x. They ask for the lower bound. Then you do comma, you give it the upper bound. Then comma, you give it your x. Then comma, you give it your standard deviation. And then you hit enter. So that's how you would type it in if you didn't have, kind of the menu screen ahead of time, which asks you to do that. Okay, so there's our probability, 0.092 something, something, something. And if we go to the answer here, scroll down, 0.0924. There it is, rounded off. Okay, so that's how we get that. Now, then they're going to ask you if it's unusually low. Well, unusual in statistics always means less than 5%. So we could redo this for 85%. So now we would just recalculate our x value for 85%. So we would take 85% of 221 and then do that. Okay, let's do this one in Excel. Now, this is a fancy template that I have because I do these all the time, and it's just nice to not have to redo it. And up here, I have our mean, right, for my population, 221 times 0.87. And here's the standard deviation, right, the square root of the 221 times the 0.87 times, Q. And then we're going to test for 85%. So down here, I know it's going to be a left-tail test. And why do I know it's a left-tail test? Because when you're testing for something to be unusual, you're looking for the area under the curve that's in the tail end of the curve, right? So the tail end of the bell curve. So if the mean value of our distribution comes from 87%, then we know 85% is going to be to the left of it, right? Because if we take 85% of 221, we're going to have less. So it's going to be a smaller number. And in fact, right here, you can see that I did 221 times 0.85, and I got 187.85. That number is smaller than 192. So when we're testing any kind of unusualness, we want to know what's the probability of being that far from the mean or more extreme, right? Or farther away. And since we're testing an x value that is below the mean, then we want the area further to the left of that. If we were testing, let's say we were asking, is 90% unusual, which would have been above the mean, then we would have to do a right-tailed test, right? So we could come up here and we'd say, okay, this is going to equal 221 times 0.9. And now that is bigger, right, than our mean. And you can see that this, because I'm using the right tail one that I set up, this gives me the area to the right of it because we're testing for being that far away from the mean, i.e. in this case about 7 points, right, or more. Well, the one that we're testing is below it, so we want that far away or less. So you're always looking for the area, the extreme, right? So you're always looking for outside of your x value. Wherever your x value lands, you're looking for the stuff outside of it. So in this case, we're looking for the x values below it. So we're doing a left-tailed test. And a left-tailed test is really easy. All we do is the standard norm dot distribution function that we have up here. And the norm dot distribution function, first it asks for our G26, right? What's G26? Well, in mine, G26 is the x value. So first it asks for the x value. See, I have this set up as a recurring formula where I don't type numbers in here. I type locations, and then all I do is I change the values in those three locations. You can see that this cell is highlighted, this cell, and this cell, because those are the three that the formula is using. And if I change those, then it just automatically changes my answer here in this space. It just saves me time. So if you want to do the formula just once, right, you don't want to set up something like this where it's recursive, it's simple. The first number you give it is your x value, the thing that we're testing, so the 187.85, then comma. Then the next thing you give it is the mean, the 192.27, right? The next thing you give it is the standard deviation, and then you say true. So it's a lot similar to, it's very similar, I should say, to the normal CDF function in the calculator. The only difference with the calculator is instead of asking for the x value, it asks for the actual range of values, right? It asks for the lower bound and the upper bound. With the normal distribution function in Excel, the lower bound is always assumed to be negative infinity. So this function always gives you area to the left of your function. So when you need area above, you just have to do 1 minus this. Because remember, the area under any distribution curve always equals 1, because probabilities sum up to 1, right? And these are probability distribution curves. So if we need the area above a value, if we take this function, it's going to give us the area below. So all we got to do is put a -1 in front of it. So for instance, the right-tailed test, this picture here, if you look at that formula, it simply just equals 1 minus the function. So I can have it do it for me there, rather than do the function, get an answer, and then have to do 1 minus that, like in my calculator or something. So you can always do these things. Now you'll also notice that when I click on my mean, instead of typing in this number, I had it calculate it for me. And same thing with the standard deviation. I had it calculate it for me. So this keeps all the numbers as precise as possible, and I carry as many decimal places as possible. Okay, so back to ours. We're testing 221 times 0.85. Again, I just typed that in rather than, calculating it, putting in a number. Keep all the decimal places possible. It gives me an answer. And there's one last thing I want to mention about Excel. Be very careful about how many decimal places are displayed in your cell. For this question, they ask you to round to 4 decimal places. So I have my cell formatted to 4 decimal places. If it wasn't, you can change it up here. Up here above number, there's these 2 little things that increase or decrease, right? So if I click on this, it's going to show less, and it's going to round as it does it, right? So it could round all the way to 0.2. Or I could show more. And the problem is if you had exactly 1 more, this 2 is being rounded by the number behind it. Now, it doesn't matter in this case, because if you were to round by 4, in your head, you'd go, well, 2 doesn't do anything, so my answer is just 18883, and you get the right answer. But what happens if the original number was, let's say, 18834.9, or even 47? Well, if you had it showing 5 decimals, that 7 would make the 4 a 5. Now you'd be looking at 18835, and you'd go, oh, this rounds to 1884. You've now rounded twice, and you have a wrong answer. So you just always want to make sure that you change the number of decimals to exactly what you want. Just put it exactly at what they ask, and let Excel do the rounding for you. It's one less possibility for you to make a simple mistake, right? So that's another tip. So there's our answer. We can go back to the question and see that it matches perfectly, 1883. And then, of course, because it's greater than 5%, right? 85% is not considered an unusually low percentage of booked passengers, and therefore there is no evidence. So if it's not unusual, there is no evidence that the percentage of booked passengers has changed from 87. We're basically saying 87 is still assumed to be true. And these are concepts that we're going to hit further on, in depth when we get to hypothesis testing formally. Okay, I'm going to stop here and let you guys finish the last one on your own, do the 82% and see what happens. You can see what the answers are supposed to be, and then go ahead and make sure that you can get those answers out of whatever technology you're using. And then you can see that this one is, in fact, unusual because it's 0.0135, right? It's just a little bit over 1%. And because it is unusual, then we say there is evidence that the percentage of booked passengers who show up on time is now lower than 87, because 82 was lower than 87. If we had tested this for, like, let's say 92%, and we also got unusual, then we'd say there is evidence that the people who show up is now higher than 87, because we were testing with a number that was higher than it. Okay, so those are the basics of how we describe our results. All right, I hope this helps, guys.